Hello there, my name is Raymond Doe, and welcome to my first Physics 2211 lab video, Lab 1 Constant Velocity. Hope you enjoy. So in this lab, I will compare the observed and predicted positions of an object moving at a constant velocity with the purpose of visually demonstrating the principles of Newton's second law of motion, which suggests that we may be able to predict the final velocity and momentum of an object to be equal to its initial velocity and momentum when moving with a net force of zero. By the end of this lab video, we'll be able to understand the physics associated with the net force and the motion of an object's velocity and position. We'll also visually comprehend how having a net force of zero acting on an object equates to a constant velocity of an observed motion graphically. Some of the relevant principles and formulas we'll be using in this experiment includes Newton's second law, also known as the momentum principle, which defines a force to be equal to change in momentum per change in time. This formula can be rewritten to predict final velocity and final momentum. This principle also holds that under the conditions of a net force equal to zero, meaning the summation of all forces acting on the object equals zero, the velocity of an object will remain constant. Thus, final velocity and momentum equals the initial velocity and momentum. One can also manipulate the formula for average velocity to predict the final position of an object in motion. Reviewing some of the materials and procedures I used in this lab experiment, firstly I'd like to account for my materials. The object I used was a simple ping pong ball. The observed position model was generated using tracker software, and the predicted position model was generated using a GlowScript computational code. For my procedure, firstly, I recorded the motion of the object rolling across a flat surface at a constant speed with no change in direction. I then analyzed the object's observed change in position over time using the video software tracker to determine linear motion, aka constant velocity. I then edited a GlowScript computational code with relevant information to generate the predicted model of the object's change in position over time. Finally, I graphed the data from both models in Excel to compare trends and was able to analyze my results and conclude data from there. Taking a look at our observed position model generated from the tracker data, you can see on the image below that I've clearly labeled the system and surroundings of this experiment, the system being the object, the ping pong ball itself, and the surroundings being all other forces acting on that system. You may also note from the red checker points following the ball that the object is moving in a motion from left to right, which is also reflected in the top right graph of your screen, as you can see that the position versus time graph is moving with a positive slope. What you may also note about this graph is while the trend is not perfectly linear, the change in position over time is almost certainly moving at a constant rate. Starting to collect some of the data that we'll need to input into our GlowScript computational code, I started by calculating the average velocity. I did that by taking the first 2 points of time and position and simply subbing them in for r and t in the average velocity equation you see below. This yielded an average velocity of 0.54 meters per second. Moving over to our predicted position model, I started by inputting my initial conditions. Simply plugging in relevant values either given to me via tracker, such as initial position and last recorded time, calculated by hand, such as the initial velocity, or just research, such as the mass of a single ping pong ball being 0.0027 kilograms, I was able to generate a pretty accurate predicted position model. While both the observed and predicted models of position appear to be fairly linear, there is a notable trend that the observed position has a flatter slope indicating a slower speed than what is predicted. This may be due to our assumptions that the net force acting on the object was absolute zero, disregarding factors such as friction and air resistance in our predicted model, which will result in this object's position moving slightly faster and explains why its slope is much steeper than observed. So what would our graph look like if I were to flip my x-axis? Simply put, if I were to change the direction of my x or horizontal motion of the object to right to left, the slope of the graph would be negative, as position graphs distinguish direction as right to left being a negative slope and left to right being a positive slope. This is represented graphically below. Is it possible for you to say how many pushes and pulls, or how many forces, are added together to give zero net force in the case that you observe? We can certainly approximate the amount of forces acting on the object at once using a free body diagram such as the one shown above. We can see that while the ball is rolling, forces acting on the ball include the weight of the object, the normal force, the pull of the friction force, as well as the force of the initial push that set the object into motion. With this in mind, when seeing how the observed model diverges from the predicted model with a net force of zero, we can come to the conclusion that the motion of the object we observed did not actually have a net force of zero. Thank you, and I hope you enjoyed.